In this video, I'm going to review thermal camera pixel size and how to calculate areas of coverage, pixel size, pixel shape, all based on the resolution of the thermal camera sensor, the field of view of the chosen lens, and the distance that the camera is from the object being imaged. So to start this off for my resolution, I'm going to use an example resolution of 640 by 480 pixels. And this is a pretty standard, this is considered standard definition, but for a thermal camera, this is a pretty decent definition camera. And the way this is laid out is this is our width by our height in pixels that the thermal camera sensor is able to detect. So width by height. Okay. And then the next is the field of view. This is the lens, and lens is going to be given in degrees. So I've chosen a lens that has a 24 by 20 degree field of view. And again, this is also, we're looking at a width by height scenario. Oops. So width by height. And then for a distance, for this example, I'm going to set a distance of 32 feet. Now, one thing to point out is when we look at these, the first thing we need to look at is our ratios, because down the line, we're going to need to know that to know whether a pixel is going to project square or rectangular on the surface. And so to give you an idea of that, in the case of our resolution of our sensor, this is a pretty standard what's called 4:3 resolution. The way we get that is that you find the highest, the greatest common denominator. In the case of 640 and 480, that's 160. So if I go into a calculator, if I do 640 divided by 160, you'll see it equals 4. And if I do 480 divided by 160, that equals 3. So that's where that 4:3 aspect ratio comes in. For our lens, however, these are not a 4:3. This particular lens arrangement, if we find the highest common denominator here, that is going to be 4, the largest number that you can divide these. And in that case, what that means, so 24 divided by 4 gives us a 6 by 5, or a 6:5 aspect ratio. So because these two aspect ratios here are not the same, so 4:3 and 6:5, they will not have square pixels. The pixels will actually be rectangular. And so that will play a part later on when we decide how big of what's the smallest feature or smallest fault or damage area that we're able to effectively examine at 32 feet of distance. So the first one I'm going to do is I'm going to look at the horizontal distance here. So let me get back into text mode, and I'm going to start by doing the horizontal distance. And so if we do the horizontal distance, I'm going to draw kind of a diagram of how this looks. And so the way this will look, if we look at it from the top, if we put our thermal camera right here, here's our thermal camera with its little lens on the front. Okay. The field of view is 24 degrees. So it's going to go out roughly like this and roughly like this. And we're going to get a horizontal distance here, and that's what we're trying to figure out. Now, we know that this distance is 640 pixels, and I'm just going to divide this in half because we're going to need to divide it in half in order to perform a little bit of trigonometry. The other thing I know is my distance is 32 feet, and I know my angle here is 24 degrees. But this, looking at the whole thing, isn't going to be helpful. What I need to do is look at half of it. So I'm going to redraw, in this case, just the right-hand half. And again, this is looking from above. I can actually make that look nicer here. Let's try that. So if I look at it just from above, there we go. Now our distance across the top, instead of being 640 pixels, is going to be 640 divided by 2, or 320 pixels. And our distance is still going to be 32 feet, but our angle now, again, instead of being 24 degrees, now is only 12 degrees because it's half of the 24. And now we can use trigonometry to figure out what this horizontal distance, what I'll call x, is. So this is we have a known, angle or distance here, and we have a known angle, and we have an unknown here. This is a tangent problem. And so we take the tangent of the angle, and the tangent of the angle is equal to opposite over adjacent. So opposite is our x, and adjacent is our distance, 32 feet. And if we move everything around, x becomes 32 times the tangent of 12. And because this is in feet, if we just do that directly, so x equals 6.80 feet. The way I got that is if I go into my scientific calculator, first of all, I want to make sure it's in degree mode, not radian. And I go 32 times the tangent of my angle, 12 degrees. Oops, 12 degrees. And that gives me the 6.80 feet. So, 6.80 feet. That also is equal to, 6 feet, 9.62 inches, or probably most importantly for this is going to be 81.62 inches. Okay. Now the other thing we can figure out from here is we know now this is 81, this top area, x is 81.62 inches. We can also figure out what the length of each pixel is. And the way we do that is pixel, it is inches, that equals inches per pixel. So inches per pixel, we take our 81.62, we divide it by the number of pixels here, and remember we're only dealing with half of them, 320. So we take our 81, we multiply this times 12, that's going to give us our 81.62. And if we divide that now by 320, it gives us a distance of 0.255. So each pixel is 0.255 inches. And that's going to be important later on because we're going to have to figure out the minimum size, or the smallest item that we can identify. And that's going to be based on a minimum pixel overlap of 9 square pixels. So this was the horizontal part, but remember this is a rectangular, these are rectangular pixels because we don't have even or equal ratios between our resolution and our field of view. So now we also have to find our vertical. And so I'm going to now demonstrate how to find the vertical pixel size. And it's going to be very similar. And so Let's add a new section here for vertical. And we're going to get our pencil back out. And so for vertical, remember our resolution now. So if I draw my same triangle again, I'm going to bring that down just a little bit more. Make a triangle. And it's not exact. It should technically be an isosceles triangle, but our height now instead of, I'm looking at this from the top, but what this is actually the height. We're looking at it from the side. So now our height, instead of being 640 now, is 480 pixels tall. Okay. And to make this easier, I will, rather than doing this, I will do it this direction. So here now, if we go up, over, there we go. Here's our camera right here. So now we're looking at a vertical. So 480 pixels tall. Okay, but we don't know how tall that is. Our distance is still 32 feet. But now our angle, where earlier it was 24, now it's only 20 degrees. So our angle here is 20 degrees. And that's for this full width. It's not, this is the full angle, not a half angle. But again, we're most interested in a half of this, a right triangle. So I'm going to redraw that. Make a nice triangle here. And again, our distance here stays 32 feet. Now our angle here, instead of being 20 degrees, now is 10 degrees, right? Half of that. And half of 480 divided by 2 equals 240 pixels tall. Okay, so we have that. And now we use the same formula. So again, because we know an adjacent, we have our angle, and we know an adjacent, and we're trying to find an opposite. We'll call this y. So we're trying to find y as opposite. We can do a tangent problem again. So y now equals, the tangent of 10 equals y over 32. Or y equals 32 times the tangent of 10. So if we clear this, 32 times the tangent of 10 gives us 5.64 feet. Remember, because the 32 is in feet, so y equals 5.64 feet. Okay. And again, we can do that with, we want to get that probably in inches is going to be the easiest in this case. So if we multiply that by 12, y equals 5.64 times 12 to give us inches. Oops, I think I hit a negative. 32 times tangent of 10 equals that. And then we'll go times 12 inches. Gives us 67.71 inches. So the height here, y, is 67.71 inches. And now we can figure out what the pixel size is again. Our pixel size, remember, is inches per pixel. So that's given by taking our 67.71, dividing it by the 240 pixels in this triangle. So the 67.71 divided by 240 pixels gives us a pixel size of 0.282. 0.282. So now we have our pixel, each pixel at 32 feet. If we draw our pixel, remember our pixels now are going to be slightly rectangular instead of square. Our x is, they're almost square, but they're not quite square. Let me see if we can get to turn it into a rectangle for me, a nice clean rectangle. There we go. So our pixel, our width on the pixel, our horizontal is 0.255. Inches, and our height is 0.282 inches. And that's our pixel size. So now what we can figure out is what is the smallest object that we can see, or the smallest feature we can see. And remember, the feature that we see is we have to overlap our whatever we find by roughly a 9 by 9 or a 3 by 3, a 9 square pixel grid, right? So, if we multiply each of these by 3, the 0.255 times 3, 0.255 is just going to be a little bit over 0.75. It's going to be 0.765. So 0.765 inches. And then our height is 0.282. 282 times 3 gives us 0.846. 0.846. And so if we typically assume we're looking for something relatively square or relatively circular. And so we have to go with the larger of these two. So effectively what we would say is, the smallest roughly circular damage or area I'd be able to find at this distance of 32 feet would be 0.846 inches. And that's the diameter. Okay? And that way it would be, if we overlaid our grid on top of it, there would be 9 pixels, or a 3 by 3 grid that would find that object. If we need to find something smaller than that, if we need to find an object that's 0.5 inches, we would have to move closer. And in the next video, I'll work backwards to show if we know what size our flaw is, then we can figure out how far away we can be while we're imaging, and that directly affects how quickly we can image a object based on its total overall size.